Hello friends, today I am going to talk about maximum likelihood estimation, a statistical estimation technique developed in early 1900 by Sir R. A. Fisher. So let us start with a sample of size n denoted by x1, x2, xn. We assume that we know the underlying distribution f, which depends on a parameter theta in the parameter space capital theta, where theta is unknown. So we know the distribution, the structure of the distribution, but only the parameter is unknown. So we need to estimate this parameter theta. So with this context, given the sample x1, x2, xn, we define a likelihood function of theta as follows. We denote it by ln theta, n because of sample size n, which is product of fxi theta, assuming the samples are independent and are identically distributed. So we define the likelihood function ln theta as product of fxi theta, and we look at it as a function of theta. So this is a change of perspective, because we are not looking at the function as a function of x. X's are given, the observation has happened. Now we are looking to the likelihood. Sometimes we take log for mathematical easiness, and we consider the log likelihood. So the maximum likelihood estimate of theta is given by the value of theta that maximizes the likelihood. Ln theta. Intuitively, maximum likelihood estimate of theta is the value of theta for which the observed x1, x2, xn becomes most probable. There are huge literature on the properness of this assumption, but this is the way we define maximum likelihood estimate. So mathematicians like Gauss, Laplace, Thiele, Edgeworth used this concept of maximum likelihood estimate, but it was Ronald Fisher who, between 1912 and 1922, single-handedly created the modern version of the method. So it came from Fisher's idea. Some more of history. Maximum likelihood estimation finally transcends heuristic justification in a proof published by Samuel S. Wilks in 1938 that is known as Wilks' theorem. Wilks showed mathematically that log likelihood, the error distribution, is chi-square, and that helps us to think about the confidence interval estimation of theta. So this is because of this Wilks' theorem in 1938, MLE, the maximum likelihood estimation, found its ground truth. Some properties. Consistency. As the sample size n increases, the maximum likelihood estimate converges to the value of theta weakly, or under some regularity conditions we can show that this convergence is almost surely convergence. We rarely have small sample properties of MLE, but maximum likelihood estimator has good asymptotic properties. One of them is consistency. Then comes invariance. So if for a transformation g of theta, if we want to find the maximum likelihood estimate of g theta, it is only the g of the maximum likelihood estimate of theta. This property is less commonly known as functional equivalence. This is called the invariance or functional equivalence. Finally, the efficiency. Maximum likelihood estimate achieves the Cramer lower bound when the sample size tends to infinity. So asymptotically, MLE is a very good estimator, This means that no consistent estimator has lower asymptotic mean squared error than maximum likelihood estimator. Since we know the Kramer bound is attainable, MLE is one of the best estimates of parameter theta. I'll stop here. Thank you.